Cuando hablo de sacar la ecuación de cortisol, como que creo que hice bien la semana, pero eso depende. Sí, pero no sé cómo sacarlo del producto. Eso todavía está. Eso se me salió bien.
Sì, senti qualcosa?
Sí, creo que esto.
Prova 1, 2. Dovresti sentire. No.
Pero no sé, pero creo que lo único es esto.
Prova.
Sé más o menos qué sale, pero no sé cómo justificar, no sé cómo derivar.
Well, because he put the coordinate system.
Non senti? Adesso non senti?
No, we don't have the time. We will start this spin tool.
Ok, va bene.
When
Bene,
you
ciao.
learn this.
Pero no sé cómo sacarlo.
I was in QFT.
Okay, I just started it just to. No, not yet.
I started it yesterday and I got an answer. But the problem with these questions is I don't know.
No. Es porque básicamente es el dado armónico. Pero con el debería ser un semicolor.
ماشي نو ناخذ اكل دي
طبعا ايوه
message to all other universities.
Sì. Sì, ma perché tu hai il volume là piano. Anche sulla pagina. No, perché qua io sentivo molto.
Yeah, sorry.
I gave up. I'm an easy guy. I give up.
Just change this. People are already waiting. Can you get it? What it is? It's gone.
Ahmed confidence is rising rapidly from Saturday.
Yeah.
So, do you know the reason why?
Okay.
Oh, really?
But you didn't care before.
I don't
You didn't even come.
I don't think that.
Because you're already in.
No,
You don't care.
even before.
Shut up.
No, you were freaking out.
So do you know the reason why young teenagers in
Bene. Ok, bene, grazie. Ciao.
animal costumes?
Have you figured it out? Why?
I asked my friend. He said Chinese New Year, but why?
Why would EST people celebrate Chinese New Year?
The carnival guy. Which carnival? Which carnival is it?
No.
No, it's carnival forward. What carnival? Carnival. I know the
we have a race.
Yeah, the thing is at Carnival it's a Catholic thing because you can like rave on the ship before the like a period starts because it is done 40 days before Holy Week.
Just like
in the
animals
Philippines,
only.
we don't
So this is I
celebrate.
think that's just
Don't
specifically from here.
celebrate the
For example, in
carnival.
Venice they wear these masks. In Rio de Janeiro they don't wear shit.
Wow. Because I mean,
And in the Philippines, it's Ash Wednesday.
Yeah, Ash Wednesday, like the
We-
Tuesday
we-
before is the actual
Yes.
carnival because it's the
yes,
last
I know
day.
that this is like the
And
Venice,
we don't
the
celebrate.
Venice Carnival.
Lent in the
this,
Philippines is very solemn.
No.
You have a carnival in your country? Like this?
No, it's a carnival. It's a carnival every day.
Just like jumping with people trying to survive. I mean, we had some rain yesterday
Wow.
because
So how you spend the
because the temperature dropped
Valentine's Day?
and because of the rain was
Yeah, Valentine's
3
Day
millimeters over Cairo.
Okay.
The whole is next.
25 years on this freaking earth.
The underground stuff
I've never
Oh
thought
my
about
God.
working.
Because I guess you don't have the good drainage
I mean,
system, right?
if you have,
Okay,
I mean,
the electricity feeders were
It's
not
not
isolated
just
and
something
everything
to
went
do.
on fire.
Oh
I
my
mean,
God.
I think it's
Hmm.
50 Shades Green is showing. But I mean, you want to spend your
Vulgar and more vulgar
No,
every day.
I'm just kidding.
Alex in 50 Shades, not person.
No, you don't have a grade for mental scores. You'll have it later. He's getting a full score, 5 out of 5. And we're getting minus 5 out of 5.
I think
Minus? Yes, it is a minus reason.
He will be so angry.
I mean, the assignments got them very good, so I sent like 2 maths already. That I put all other than
I'm looking around the internet just to make sure.
Yeah.
I'm getting lazy now.
I think what's your thing that we have a field?
Because he said,
what
What's your thing?
because of the question.
No.
No, what is your question?
Field outside of our field, right?
The energy momentum tensor
The tensor of the
outside.
field. No, the field.
That was an
The
example.
differential equation.
It was an example.
Differential and the field.
yeah,
We got the
I
field.
mean,
No.
Just instead of y, just put theta equation.
it's just saying that.
Differential equation. And just
It was just an example.
No, it's obviously if you're not taking the average, you'll find that TAJ is 0.
TIG outside the box.
Outside the box, once it hits the walls,
Yeah.
spike.
And the example was the derivative is 0 of TIJ, and the TIJ outside the box is 0. So if the derivative is 0, so it has to be 0 inside as well. That is what he was explaining.
Well, I know that the
That is fine.
connection between the agent and the field is fine, so.
No, phi, there is no field. I mean, it was just an example.
Phi,
It is phi, the function.
The delta phi. What is the TIJ in the delta phi? It's d mu phi, d mu phi. So I think you would find the.
No.
I mean, you can, as a thinking of it, you can always use one of the identities of TIJ, express TIJ in terms of T00 on the x-axis, and you'll find that it's essentially just T00. You take the average minus mu. That's another way.
Shut up. I'll kill you.
I watch it.
It's bad. You won't understand because you're already in. Shut up. You at least know someone is interested in you. But it's still better than CSAT. Just imagine this is this course. What about the courses in CSAT? They will be insane.
I mean, it's what's better. Watch the
How?
movies. But it's usually the card games that I watch highly randomized.
Yes. So
So what happens is that in one turn, things can go from
the
good
QFT
to
will
bad
start
in
from
one turn.
renormalization group.
People are very smart.
Okay, we will have that with say. Okay, I have a question. When are we having the exam? Because we just have one more week after this week.
So the last week of classes will be, thank you. The last week will be,
Next week.
no, I think we have more. The last week is the last week of February.
No.
Yes.
We
Why
have
not?
15 lectures
15
for you, and this is the
And
fourth week.
tutorials are not counted as tutorials, they're counted as lectures, according to the website.
Okay, forget about the website. I'll teach until the 2nd of March, which is like a Friday, I think. Maybe their exam can be on that Friday, but I let you know. I go until the
2nd of March.
2nd of March.
Okay.
Okay, because the website says that
Your course ends next
Professor-
Friday.
Professor's
Okay.
follow will start on the 27th.
No, that's not correct.
Okay.
So yeah, either it depends how it goes. Either the exam will be on that Friday, which is 2nd of March, or I'll finish by then, and then the exam will be the week after.
Okay.
I won't be here the week after, but then somebody else can give the exam. Which means 2 more weeks, right?
Yes. Then yes, 2 more weeks.
Sorry.
La página de Untitled Chapter. Va a seguir dando clases hasta el 2 de marzo. El examen puede ser el 2 de marzo de la semana que viene.
Okay, so far we discussed relativistic scalar theory for gravity. We talked about its phenomenology, and we saw that it fails to agree with the observations. So we should move on, consider other possibilities. we said that the force carrier for gravitational force has to be a massless particle because it is a long-range force. So we tried the scalar particle, spin 1 part, massless spin 1 particle is, gives rise to something like electromagnetic interactions, which is not a good candidate for gravity because it gives repulsive force between positive charges. While we know in gravity, positive charges, which are positive masses, attract. So spin 1 is not a good option, so we naturally go to a spin 2. So we should write a relativistic theory for a spin 2 particle. And that will be described by a field h mu nu, which is symmetric.
I have a question. From what we did at the beginning, the representations of the Poincare group, how do we go from there to the fact that it has to be described by a symmetric tensor field?
That's a very good question. It's a bit hard. The fact that, so this is something that there is, I have one, I think I give one exercise in the notes that tries to explain this or show what is the main idea. So the main idea is that yes, we talk about representations. We say that we have a spin 2 particles, and now we want to write interactions between these spin 2 particles, or spin 2 particles and other degrees of freedom. Now, this step of going from different particles, different asymptotic states to fields like h mu nu phi. This step is required by the requirement of macrocausality, or a related thing is that if you want the S matrix to be Lorentz invariant. So there are a bunch of conditions. We want cluster decomposition, which basically means that if you do 2 experiments far away from each other, the results should not affect each other. So that combined from the requirement that you want a scattering matrix which is Lorentz invariant, that implies that the interaction. So you basically write some interaction Hamiltonian between different degrees of freedom. So let's say I introduce creation and annihilation operators for these different degrees of freedom. Let me just put some label R for this. So you write some Hamiltonian for these different creation and annihilation operators which depend on momenta and spin. Another question is how to build this interaction Hamiltonian between different particle degrees of freedom. As far as we are talking about free particles, there is no, this doesn't really matter. What is important is how to describe interactions, and that's when we have non-trivial scattering. That's when we want to ask the scattering to have good properties under Lorentz transformation. That implies that this interaction Hamiltonian has to satisfy this principal microcausality, which means that if you Fourier transform this to position, then the interaction, the commutator of interaction Hamiltonian has to be 0 if x minus y squared is larger than 0, basically when they are space-like separate. This is the natural expectation in a relativistic theory. To a space, there shouldn't be any effect at a space-like separation. So once you require that, there is some argument. You can see it in Weinberg. I think section chapter
Are there
5.
other references besides Weinberg?
But I think that's the only place that I have seen the argument. I don't know. The argument is not a rigorous proof, but it's a very good argument that indicates, at least it guarantees that if you work with local fields, with right transformation, so if you put these particles inside fields with right transformation properties under Lorentz, then you are guaranteed to satisfy this microcausal. So that's when you decide that the spin 2 particles have to sit into a representation of Lorentz, which is like a 2-index representation of Lorentz.
Still, it seems like using fields is sufficient but not necessary to satisfy the causality.
Yeah, I'm not aware of a proof that it is the necessary condition. But as I said, there are good arguments that why it might be the case. I would say it's almost a proof, but not quite. There is a homework in which I try to put in some of the main ideas. I don't know if it is doable or not. I mean, if it is doable before reading Weinberg. After reading it, it is doable. Okay, so we have to construct a field theory for this symmetric tensor, and so we immediately notice some redundancy, which is that now this h mu nu, symmetric h mu nu, has 10 components, while we know that there are only two independent gravities. So if I fix momentum, then we have two polarizations. So somehow we have to go from 10 components in this h mu nu to 2. And there is a similar situation if we talk about a photon. We describe photon using a vector field A mu, a Lorentz vector, and that has 4 components, while we know that there are only 2 polarizations of photon. I mean, one way of justifying this is a posteriori, of course. You can just follow the same procedure. We know that for Maxwell theory, we can write an action using a 4-vector with some gauge symmetries. Now we can try to write an action for a 2-index tensor, and we get the right answer. We get massless spin 2 polarization. So it works. Okay, so yeah, so the task would be to do something similar to Maxwell theory. So what happens in Maxwell theory is that we work with this 4-vector, which has redundancy, but we write a theory that has some extra symmetry, called the gauge symmetry, for an arbitrary alpha. Alpha is some arbitrary space-time space-time variable. And once we do that, this implies that the equation of motion for A mu will depend on F mu nu, the field strength, which is invariant under that. So we write the Maxwell action, which is constructed out of this F mu nu, which doesn't change under this gauge transformation, and we get an equation of motion which looks like this. Now, this F mu nu is by construction antisymmetric, which means that d nu F mu nu is equal to 0 as an identity. So this is identity. That implies that whatever source that we put on the left-hand side, that has to be conserved. So we are not allowed to write arbitrary sources in the Maxwell theory for electromagnetic. So a similar thing happens for H mu nu. We can either discuss construction of an action or writing an equation of motion that satisfies now a bigger gauge symmetry, which is H mu nu going to H mu nu plus d mu xi mu plus d mu xi mu, where xi mu is an arbitrary 4-vector now, depending on coordinates. So we can try to write a quadratic equation for this H mu nu field. Remember, this is a second order equation for A mu field. So if I open it up, it will be box A mu minus d mu A mu equals J nu. Sorry, no. Mu mu. So it's a second order equation of motion for this A field. So similarly here we can construct an equation for this H mu nu. Naturally I will start from writing box the version of H mu nu. But then there are many more tensorial structures that can be added to this equation. So for instance, I can write d mu, d alpha, h alpha nu with some coefficient, say a1, and then many more. And then we have to put a source on the right-hand side of the equation. Again, the source should be looking for a conserved source in analogy with that, or it is also implied by this gauge symmetry. So we need a conserved source, and since we want to describe gravity and we are looking for a conserved source, that's the most natural option. In fact, the only option is T mu nu. But here, by T mu nu, okay, so now we are constructing a linearized theory for spin to gravity, which means that if I have this H mu field here, this T mu nu is that of the matter field. It's a similar idea as in the case of dilaton gravity. If you remember, there we had box phi equals 4 pi g times the trace of a stress tensor, but this trace of a stress tensor was the part that comes from the matter field, because we were talking about linearized theory of the phi, so we didn't include the stress energy tensor of phi inside this T mu mu. That would be a construction of a nonlinear theory for phi for a scalar graph. So this was just for as long as we care about linearized theory. Here there will be matter. The same thing here. There is this. So what are the unknowns in this equation? The unknowns are these coefficients that sit in front of different tensorial structure, and then this proportionality coefficient. These ones are basically fixed by the requirement of gauge symmetry. And then this overall conservation. A more precise way of saying that is that there are actually two tensorial combinations that are invariant under this these are called linearized diffeomorphisms, or linear diffs. So there are two linear combinations that are invariant under linear diffs. We can combine them together with the right, take the one combination of those two structures so that it is similar to F mu nu. It is automatically transverse. So let me call it so this epsilon alpha beta mu nu is an operator, is a differential operator. For instance, the first term is just delta alpha mu delta beta nu times box. And then there will be others. So you can see that when it acts, when I multiply this by H alpha beta, it reproduces the first term here. And then there will be other combinations of these derivative operators and Kronecker symbols that reproduce other. Okay, so there are two combinations, and I can combine them together in the right way, so that this structure is identically conserved. Meaning that if I take the mu of this, that is automatically 0, regardless of what it acts on. So I can put some H alpha beta here. But regardless of what is H alpha beta, there is a structure that when I add by d mu, it is equal to 0. This is very similar to what happens for the field strength. That is, this equation is satisfied regardless of what is A mu. It's just a consequence of antisymmetry of F mu. It's the same story here. This will be 0, and then this the source in that equation is the only candidate that we have, the stress energy tensor that has to be constant. So
why are you saying that you have two different equations and you have to combine them? Why do we have two different equations?
Well, I'm saying not two equations. We have two. So here I'm writing different tensorial structures.
Yes.
What I'm saying is that there are two different tensorial structures that are invariant, separately invariant under linearized diffs.
Okay.
So I'm just saying that you can combine them together with the right coefficients so that
they're antisymmetric under mu.
They are not really antisymmetric.
Okay. But
you see, for instance, this term is not antisymmetric, but it has the property that it is identically conserved.
Okay.
And this is easy. One of the structures is actually a scalar. It's just d mu, d nu, h mu nu minus box h mu nu.
Yes.
So the claim is that this combination is invariant under linearized diff.
Yes.
Maybe you can check it now.
Okay. Yes. Yes, it stays in memory.
Okay.
Cancel out, so
Sorry, can you raise it to continue that pictures? The Hito cancel that. Sorry, can you raise it to 783?
Yes. So yeah, if we do this change, this goes into d mu times. Let's just write the variation because it's a linear. So I only write the variation. Here I get d mu xi mu plus d mu xi mu minus box the trace of this object, which is d mu xi mu with a factor of 2. So that's the change, delta of whatever it is. And then I just take in the derivatives inside, and it gives me twice box d mu xi mu minus twice box d mu xi mu cos 0. So yes, so there is this combination whose variation is equal to 0. There will be another combination. So this is a scalar combination.
yes.
There is another tensor combination whose variation is 0. Of course, you can combine the two using the Minkowski metric, right? So I can call this, I don't know, this guy R. And then the other combination we can call R mu nu. So this is R1 mu nu, and then you can combine with some coefficient times eta mu nu R1. And there is one good choice of A, so that the total object that you get is identically conserved, meaning that this is equal to 0, regardless of what is H. So that fixes, this requirement fixes A to be 1/2. And then, so that would be the combination that has to be equal to something times T mu nu. Since it is conserved, then we have to put a conserved source. The conserved source that we have with 2 indexes is T mu nu. But at the moment, these R's are just names. Don't worry about it. So yeah, so then the task would be, well, first of all, we can write, once we have the equation of motion, once we determine this operator, we can write the action that gives rise to this equation of motion. Similar to here, when we wrote this equation as a relativistic version of Newton's Newtonian gravity, we could write an action that gives rise to this equation. Here is the same thing. We can write an action. There will be some ambiguity because I can always renormalize, not in the quantum sense, just change the normalization of H, and that changes C. So I have to fix that. I fix that by assuming that the coupling between H mu nu and sources is minus 1/2 T4x H mu nu T mu nu. And then there will be a quadratic action for H mu nu itself. There will be some S of H or S gravity, quadratic. And once I know this differential operators, writing the quadratic action is very simple. Which is, I mean, it's an analog of what we have here. If I have the equation of motion, which is box 5, equals something, the action would be, the quadratic action for phi is, well, the easy thing to do is to just write phi box 5.
Yeah.
So when I vary this with respect to phi, it gives me this equation of motion. It's not in the first order form. It has 2 derivatives acting on a field, but we can do an integration by parts and ignore the boundary terms as usual, because the boundary terms do not change the equations of motion, and get to the usual equation. Except that there was some constant here, so that if I do an integration by parts, this gives minus kappa over 2 d phi squared. And then there was a coupling to the trace of T mu nu. So here is the same thing. Once I have the equation of motion, and once I fix the normalization of H by saying that interaction is this, then the quadratic action for H is fully fixed up to boundary terms. So that quadratic action is going to be 1/4c times integral d4x h alpha beta epsilon alpha beta mu nu h mu nu. So if I add up these two actions and do variation with respect to H, I'll reproduce that equation. So the task would be to determine C as before, as in the case of dilaton gravity. Determine C using, or there determine kappa using the non-relativistic limit, using the requirement that in the non-relativistic limit we should recover Newtonian gravity. Once we have that, then this action tells us what is the energy content of waves in h mu nu. So that's, for instance, one interesting question that we can ask. We can consider some time-varying system like a binary, and that time-varying system emits gravitational wave. Now it emits h mu nu. Before it was emitting phi in a scalar gravity. Now it emits h mu nu. Far away, those waves is going to look like plane waves. We can look at this action and see what is the energy content of those plane waves, what is the energy flux, and integrate that energy flux to get total power or luminosity. Okay, so let us determine C. And again, the easy way to determine it, the more particle physics way of determining it is to look at the interaction between two sources. Just a one graviton exchange interaction between two particles, and then take the limit in which these two particles are non-relativistic and reproduce the 1 over r squared potential with the right coefficient. That is one way of fixing this C. The other way, the easier way probably, is to look at the point particle action. And that allows us to make a relation between a component of H00 component of this and Newtonian potential. Once we have a relation between H and the Newtonian potential, then we can look at this equation and require that in the non-relativistic limit it reduces to the Poisson equation with the right coefficient, which is like G, 4 pi G. Okay, so let's look at the point particle case. We know that the T mu nu, so this is the point particle. We know that the T mu nu for a point particle is given by minus m integral d for x. Right. So then I can write this interaction between for the point particle. That is 1/2 m integral d for x d tau h mu nu x dot mu times delta 4 of x mu minus x mu of tau. So I can use this delta function to do for the integral over the space-time, and that gives me an action that lives on the word line. So I can add it to the usual free part of the point particle action. And again, I go back to the parameterization in terms of some variable sigma, because now we want to do variation with respect to x mu. So there will be minus eta mu dx mu d sigma dx mu d sigma times 1 1 plus x dot mu sigma dx mu d sigma divided by minus 2 eta alpha beta dx alpha d sigma beta d sigma times h min. Which can be written up to terms of order h squared. I can absorb this term inside the square root. So if I do that, I will get minus eta mu nu plus h mu nu dx mu d sigma dx mu d sigma plus order h squared terms that we are ignoring anyway. Right, so if I take this expression and expand it for a small h mu nu, I will reproduce this term plus some order h squared terms. So now that we have the point particle action in the background, so remember what is the logic. The logic is that we have this point particle and it moves in some background field h mu nu. And so there will be, we have this interaction term in the action. In the presence of that background field, the motion of the particle will be changed. We derive the equation of motion for the particle. We take the non-relativistic limit and see what is the force. How the force due to this background field is related to h mu nu. And compare it with the Newtonian result. We know that in the Newtonian case, the force is just given by minus m times gradient of phi, the Newtonian potential. So once we compare that result with what we get from this action, then we can find a relation between h and phi. So the next task would be to derive the equation of motion from this action and linearize it and then take the non-relativistic limit. So I'm basically following the same steps as in the case of scalar gravity.
Why did you choose that coupling between the particle and the background field?
This one.
Yes.
I'm just writing this interaction. Right, we decided that the source has to be T mu nu because we need a conserved source, and then the coefficient is just a matter of normalization of A. Why did I choose this normalization? Exactly because I can absorb it so that I can write it like that for future purpose. Okay, so we want to derive the equations of motion from that action. That is easy. So we are going to get d by d tau. No. So what are we going to get? And then the other term will be 1 half mu delta dxi by sigma dx delta is sigma divided by the same square root. Yeah, I think it's correct. So we get this equation. Now we want to take the limit in which h is small, and at the same time the velocities are small, so that we get the non-relativistic limit. Okay, so in order to do that, before that, I want to also make some gauge choice, which is that I want to go to a gauge in which h0i is equal to 0. So as we said, there is some symmetry in this problem. I can do this linearized diffeomorphism. So what is the meaning of this statement? The meaning is that imagine I start from h mu nu, which does not satisfy this equation. Then what we can do is that to do one of these gauge linearized diffeomorphism, so that the new h0i is going to be the old one plus d0 xii plus di xi0, right? And now I can, and we said that these xi's are arbitrary parameters. So in particular, I can choose xi0 to be 0 and xi or d0 of xi to be minus h0i. that implies that h tilde 0I is going to be 0. So I can choose a gauge, meaning that I can do one of these linearized diffeomorphism to set to 0I components of the field everywhere. So then this equation becomes easier when there is no 0I component. So for instance, on the right-hand side, I will have either 0, or ij components. The ij components, if I'm taking non-relativistic limit, will be proportional to v squared. Right? Because now we have velocity dxi d sigma here. Actually, another thing that we can do is that in these denominators, so there is that combination eta plus h, but I have already one factor of h here. So this eta plus h can be just replaced by eta. That makes, so let's do that first. And we can divide the whole expression by another one of these square roots. That makes the equation look like d by d tau of eta mu nu plus h mu nu dx nu by d tau equals 1/2 d nu h alpha beta dx alpha d tau dx beta d tau. There will be some additional terms which are proportional to h times this dx, but as we will see, they will be negligible anyway. So this is not, there will be some other term here. Maybe let me just keep it for the moment. Okay, but let's look at the right-hand side. So here we get the factors of velocity if I look at the ij component. So that would be suppressed because it's proportional to v squared. So therefore for alpha and beta we choose the zeros component. And then let's look at, what is this mu? Let's look at the component mu of this equation. That implies, if I look at mu component, by looking at this equation, we see that the acceleration, the Newtonian acceleration is going to be proportional to h. So that implies that whenever we have h multiplying this equation, we have to ignore it. So there will be something like, here I can have hij multiplying dxj d tau, and again d tau of that. So this is a velocity multiplying hij. That is again negligible because we take both h to be small and velocity to be small. So these terms will be neglected. What remains on the left-hand side is just xi double dot as usual. And on the right-hand side we get 1/2 di of h00. And then we can try to match it with the result from Newtonian gravity, which tells us this has to be equal to minus di of phi. So this says that h00 is equal to minus 2 phi. Any questions so far? So here the key point is what is the to identify what is the term that survives in the limit, of course. And the idea is similar to what we were doing before. We get acceleration because we are moving in this field, but the field itself is small, therefore the acceleration is small. So whenever we are multiplying h by the acceleration, that would be a second order effect, so that is negligible. The velocity itself is small, so whenever I have v times the field, that is negligible, because both the field is small and we are taking non-relativistic limit. So there are corrections to this, but they are always either of order h squared or of order h times v. In fact, probably there is not even h times v. Probably there will be something like h dot times v, or h times acceleration. So these are the kind of terms that have been dropped to get this. So we found the relation between 0, component of h and the Newtonian potential. Now we can determine this parameter c, because we can take the equation. We can take this equation of motion for phi and put a non-relativistic source and set c so that we get the Poisson equation. And we get the Poisson equation for phi. So that implies that c has to be equal to 16 pi g. 16. Yes. And once you have c, then we know everything about this linearized theory or the quadratic action. For instance, we can consider the stress energy tensor of plane waves and ask what is the energy flux. So as we will see, the plane waves can be described in terms of that. At the end, we are describing this spin two polarization. These two polarizations of gravitons using this field. These are transverse polarizations. We can choose an appropriate gauge in which they will look like. If for instance, we have k that is omega times x hat, then we can choose a gauge in which h is going to look transverse traceless on a space line. So what we have is that h y is equal to hzc equal to something h that I call h plus times h plus, which is a function of, since it is moving in x direction, it is a function of t and x. And then the other independent component will be hyz equals hz by, which I call it h cross of t and x. And then this complicated action, when I consider if I plug in a configuration like that with all other components of h equal to 0, that complicated action simplifies to an action of this form. So let's just write it for h plus. It will be h plus dot square minus h plus prime square, where prime is derivative with respect to x. So it becomes identical to a free scalar which moves in the x direction. And then we can derive the stress energy tensor for this free scalar and see what is the energy flux. Basically, we can look at the, I call it, so let's call it, how do we call it? I have two T's now. Let's call it like this. So this is the stress energy tensor for this H field. I can calculate that and look at the xt component of it. That would be the energy flux. Which is going to be 1 over 16 pi g h dot square. After I use the fact that h dot is equal to minus h prime for a right moving ray.
Can you repeat the last part? Because I didn't understand.
This part?
CXT.
So what I'm saying that there is this quadratic action. We fix the normalization of the quadratic action. Now imagine you had a quadratic action for a scalar field. With some coefficient k. So here we knew how to derive the stress energy tensor. And then if I consider some plane waves, so this action has a free vacuum, not vacuum, free propagating solutions which are plane waves, right? Because the equation of motion for this field is going to be box phi equal to 0 in the vacuum. So plane waves are solutions of this equation. Then you can ask what is the energy flux carried by plane waves here. And how would we answer that? We would calculate T mu nu, the stress energy tensor for this phi field, and looked at the 0I component of that, because we said T00 is energy density, T0 mu is the nodal current associated to time translation. So therefore T00 is just energy density, rho, and T0I is the flux of energy. So if I have a plane wave and calculate T0I, I get the flux of energy. What is this T mu nu? T mu nu of this system is very easy. You just minus kappa d mu phi d nu phi, or maybe it's minus here, plus 1/2 eta mu nu times d phi squared. And then if I want to ask what is T0I, that is going to be kappa di phi d0 phi. Right? So that's what we did for the dilaton waves. We said that we have these scalar waves, that's how we calculate the energy flux. Now I'm saying that here the problem becomes almost identical to that once you consider this transverse polarization. So as we will see in the next lecture, if you want to ask about plane waves, so ask the same question for this theory. This is a theory that admits plane wave solutions if you have no source. So when we put sources, there will be emission of waves. Away from the sources, we have basically this equation, epsilon acting on H is equal to 0, because they are just propagating in vacuum. So you can consider plane wave solution of this equation. You can use these gauge symmetries or linearized diffeomorphism to simplify the form of this H alpha beta. So the claim is that you can make it completely written in terms of these two components with all other components equal to 0. So you can write h mu nu. If you are talking about a plane wave that moves along x, then you can write it in terms of a matrix which has 0 everywhere except in the yz block. So it has h plus here, and h cross there. And then you can calculate the action for this matrix. Once you consider this configuration for h mu nu, this complicated action simplifies. It becomes like basically the same as the action for a scalar field, except that phi is now replaced by this h plus or h cross. And then you can follow the same procedure, calculate t mu nu for this h plus and h cross. That tells you what is the energy that is. Yeah, h plus and h cross are two independent fields. So it's like having two scalar fields instead of one, which is not surprising because as we saw, a spin 2 field has two independent polarizations. Other question? Okay, so we continue tomorrow. I graded your homework. I hope you don't get discouraged by the grade.
Last one or the
Yeah,
second one?
both are.
Why are you laughing?
Shall I?
This is the third or the second?
Third.
Let's see.
0 or something?
Oh, what?
0? Yeah.
What?
Exactly the
Did everyone get a 0? You didn't, right?
It's the coming.
Hello? You really want to know? Like what?
That's me, that's me.
We took the wrong idea from the first homework.
How did you forget?
We still have all those exams. So.
Yeah.
Thank God.
The funny thing is, I didn't submit homework 3. I got 0 and you submitted.
How much did you get in over 3? 3? You're right. What did I get 3?
Number 1. For the
Yes, yes.
Whatever, I'm happy.
Actually, I didn't get anything today.
From 2 homework, I got 3.
Let me do.
Give us another one.
Sure. Again, I'm a bad, but don't add the last one.
From 2 homework, I got 3.
Mathematics is not a problem, but he just states what he's doing, saying it, and doing it without saying what he's doing. I don't know.